Well, hello guys, here Mr. G with another video. This time we're going to be talking about electro-configuration. It's going to be a small video related to this topic for the grade 10. Previously, we learned that an atom has smaller particles, which are protons, and they are positively charged. They are neutrons, and they are electrons. Alright, we learned previously that, it is proven that in the nucleus of the atom, right in the center part of the atoms, is where we find the protons as well as the neutrons. So right here you will find the protons and the neutrons. We know that protons are positively charged and neutrons do not have any charge at all. That we learned. And this nucleus of the atom, which is the addition, let's say, of neutrons plus proton, will give the mass of the atom. That is also important to remember. Now, what is things that we learned previously? There is the electrons moving around the nucleus of the atom, all right, in orbitals kind of similar to the orbits of the planet, but it's not exactly like that. It's a little bit more complicated. Now, the way in which electrons are arranged around the nucleus is what we call electro-configuration. So the electro-configuration is no other thing than the arrangement of the electrons around the nucleus. So it's how the electrons are going to be arranged around the nucleus. That is what we call electron configuration. And it's a little bit more complicated than this, because actually we don't really know exactly where is the electron. So for this idea we came with something called orbitals, which we are going to explain just now. Orbitals are the most probable region in space in where the electrons can be actually found. For example, let's say that we have an atom of hydrogen. Let's use hydrogen as an example. Hydrogen. And hydrogen, let's say it have one proton right in the center. Okay, now the electrons, hydrogen have only one electron. That electron we actually don't really know where it could be. So we know it's moving around that, or it's going to be moving around that nucleus, but we don't know exactly where it is found, because that electron could be anywhere around that nucleus. Could be sometimes here, there, in the other place, there, and so on. So we don't really know exactly where is that electron is going to be allocated. So for this one, we came with the idea that this electron is rather going to be in a region. That region is going to be called orbitals. So rather than orbits like planet, it's going to be in a orbitals in which that we know that electron is going to be probably. So the higher probability of the electrons to be allocated in this specific orbital. So that electron 90% of the time, or most of the time, is going to be in that orbital. It could be anywhere in the orbital. It doesn't really need to be in that specific point. At a specific time in space or in time, we're going to find that electron somewhere within the orbital. But if this electron gain a little bit of energy, as you can see here, let's say absorbed energy, get excited, and then it's going to move to another orbital, which the other orbital, for example, could be somewhere here. So we say if that electron get excited, it's going to be moving to another orbital, and is more probably to be 90% of the time now with excited energy in that specific orbital. This one is to give you an idea. And there are different type of orbitals. There is energy level, and every energy level will have different orbitals, or we can find the electron in those probable energy level or orbitals. Now, the orbitals could be called S, P, D, and F. Fortunately, we're going to work only with S and P. Alright, so now we have energy levels. Those energy levels are going from 1 to 4. Let's write here energy level, also called shells. Those energy level is going from 1, 2, 3, and 4. There is 4 energy level, and each energy level will have a specific orbital. For example, energy level 1, we have an orbital S. energy level 1 will have an orbital s, which is the simplest one. If that electrons get excited, or the atom for instance have more electrons, then you'll have to go to the second energy level, which have orbitals s as well as orbitals p. We're going to speak about that one right now. And then energy level 3 will have orbitals s and orbital p, but also will have d and f, just we are not going there, right? We just not going there. And orbital or energy level 4 will have the orbital s. Okay, so now what is important? This one is the orbital s. It's like a spherical shape around the nucleus, like we represented here. This will be the orbital s. This one will be the orbital s. Okay, energy level 1 orbital s. That is what we go there. Now the second energy level will have orbital s, like we represented here with this color. This one is energy level 2 orbital s, and it have an orbital p, but orbital p does not really look exactly like this one. The orbital p will look like a shell, like something like this, in which let me do it, something like this, in which the electrons could be probably on that specific point, somewhere there. Orbital s is in 3 dimensions as well, orbital p, sorry, so it's going to be there, or let's say here, like this, or even here like this. So that will be how the orbitals will look. It means if the electrons get excited, it will move from s to 2s, but if get even more excited, it will move now to this orbital p, and let's say at this specific energy the electrons are more probably to be found anywhere in those orbitals p. That is what actually happened. There it looks like this one, like p orbitals, and if it's 3D, is in all the dimensions. Okay, now this is not that difficult. There are certain rules to represent electron in this orbital. This one, remember, is for grade 10. It's quite simple. I'm not going into big details. Now, for us to represent the orbitals, we are going to use circles. So it doesn't matter if it's S or P, we are going to represent it with circle. For instance, the orbital S is going to be one circle. Alright, this one will give one S, for example, or 2S. Every time we have an orbital S, we're going to represent circle. And every time we have an orbital P, we also going to represent with circle. So in other words, we'll have here, because it's a 3-dimension, we have 1 circle, 2 circle, and 3 circle. Alright, so this is orbital P in energy level 2, or any energy level we're speaking about. So every time you have 3 circles, this one will represent orbitals P. Okay, that is how we represent it. So every single orbital we're going to represent it with a circle. That one is the first important rule. Now, what else? Electrons are going to be represented with arrows. So for example, if you have an orbital S, and remember we represent with a circle, and we said in that specific orbital we have electrons, 1 electron, then that electron can be represented with an arrow if you want. So that means that this is an electron in that orbital S. Okay, now electrons always occupy the lowest energy level. Yes, they always come down here to the first energy level close to the nucleus before they move to the next energy level. To move to the next energy level, they either need to absorb energy or you need to have more electrons, but always you occupy the lowest energy level and therefore the lowest orbitals. Okay, and then there is a rule that says that there can be only 2 electrons per orbital. So for instance, if there is 3 electrons in this orbital S, I can only have 2 electrons, and they are going to be facing opposite direction. That is just by convention here. So this is another electron. So we can only have 2 electrons per orbitals. Okay, and then the Hans rule, no pairing of p orbitals before there is at least 1 electron in each of them. So if we go there, when we have p, when we have the p orbitals, and remember the p orbitals are going to be 3 circles, guys, 3 circles. The p orbital will have 3 circles because we're representing each of them. So this one is the 3 circles, okay? So p orbitals always will have 3 circles. Let's fix this one here. Try to mark it. You can make squares if you want, but doesn't matter. And let's say you have, for instance, to represent 5 electrons in this specific orbital p. Alright, so what we are going to do? We do not pair the electrons. Electrons repel each other. They don't want to be together. At least they must. So there we are going to represent 1 electron here, 1 electron there, and the other electron there. So first I'm going to make sure I have 1 electron in each of the p orbitals, and then I'm going to repeat up until I have 5. So 3 electrons, then I'm coming to the first one, I add another electron here, and then the next one another electron. So I have here now the 5 electrons. Alright, so that is the correct way to do it. And then using the electro-configuration, these drawings and these rules, we are going to have something that we call the Aufbau diagram. Now, the Aufbau diagram is going to be all the energy levels of shell and the orbitals in each of those energy levels, okay? So we have here, for example, this one is energy level 1. So this one here will represent energy level 1, which have 1 orbital s. All right, the second one here will represent the energy level 2. Energy level 2. And energy level 2 has a orbital s as well as orbital p, so 3p orbitals, which we are going to represent with 3 circles or 3 squares. Then we go into energy level 3. Now energy level 3, guys, is a little bit more complicated than this picture. In energy level 3 you will have an orbital s, you will have 3 orbitals p, you will have d and f, but we are not going so far because we are only going to work for the first 20 atoms. So we are not going to be needed either d or f. And then after energy level 3 we come in with energy level 4. So energy level 4. This is how it looks, and it's how we are going to represent any of the atoms from number 1 to number 20, or even some ions. Okay, so now to draw the Aufbau diagram, we have to follow also certain rules, and it's quite simple. We need to determine the number of electrons that the atom has. Important number of electrons, because we have to represent electrons in each of these orbitals. So we represent electrons there, right, with arrows, as we explained right here. Second, fill the s orbital first, and then you go to the second one. So you always start from the 1s before you go to 2s, and then before you go to 2p in that specific order. And then put 1 electron in each of the p orbitals before you go to the next one. We already explained that one, and let's see one example. For example, let's go to oxygen. Now oxygen will have 8 electrons. So how are those 8 electrons allocated around the nucleus? All right, so we are going to go to the 4 energy level, and we are going to do it in this way. We have energy level 1 with the orbital s, and we are going to have 1 circle. The second is energy level 2 with the orbital s, and we have another circle there. We have energy level 2 with the p orbitals, and it has 1, 2, and 3 p orbitals in energy level 2. Then we go to energy level 3 s with 1 and 3 p, which have 1, 2, and 3 orbital p, and then you may go to 4p if needed. Alright, so we have to represent 8 electrons here. Remember, you don't go to energy level 2 to orbital s in the energy level 2 up until the first one is full. So using arrows, I'm going to draw here 2 electrons, 1 and 2 electrons, and when it's full, then I'm going to the second energy level. I still have more electrons, so I'm coming here and I say 3, and 4. So before you go to orbital P, you make sure the orbital S is full, and then you go to P. But remember, in P you have to make one in each of them before you start over. So it's 4, and I'm going to say 5, 6 and 7. Only now I can go back to the first P and I say 8. And this one is the electro-configuration of oxygen. In other words, this is the probability where we can find the electrons around the oxygen atom or around the nucleus of oxygen atom. We have those shells, those orbitals, and we can see, or we can find the electrons at that specific point. Quite simple. It's very, very easy. Now, there is something called spectroscopic notation, in which we do not represent circle. It's not a Aufbau diagram. In this term, we only represent the letters and the numbers. Now, for the spectroscopic notation, we're going to say 1s. In energy level 1 orbital s, we have 2 electrons, so we say to the power 2. In energy level 2 orbital s, we have another 2 electrons. In energy level 2 orbital p, we have, or orbitals, because there are many, we have 2, 3 and 4 electrons, and this one is what we call spectroscopic notation. And this is all about the electro-configuration you need for the gray 10s. Now, do you want to represent another example? Let's, for instance, go to a magnesium. Magnesium has 12 electrons. So let's represent magnesium here, just for example, to finish. Let's go to a new page here and let's say magnesium. We are going to represent magnesium. It's Mg, and magnesium will have 12 electrons. Alright, so how do we represent here? We come to energy level 1 orbital s, that is one circle. We have energy level 2 orbital s, that is another circle. This energy level 2 orbitals p, we have 3 circles because there are 3 orbitals there. Okay, then we go to energy level 3 s with 1 circle because it's 1 orbital. Energy level 3 p, which have 3 circles. And then before we go to energy level 3d, which we don't do anyways, we go to energy level 4 orbital s, and we have to represent the 12 electrons in this specific way. So we represent the first 2 electrons here. We have 1 and 2 electrons. We go to the second energy level 3 and 4. We go to the third, to energy level 2 orbital p, and remember we represent one in each of them. So it's 1, 2 and 3. So we have 2 and 2 is 4, 5, 6, 7, 8, 9, 10. Then we need to go to the next one, which is 11 and 12. This one is the electro configuration for magnesium. I hope you understand. Now, if you want to do the spectroscopic notation, all you have to come here and say is energy level 1 orbital s with 2 electrons, so it's to the power 2. Energy level 2 orbital s with another 2 electrons. Energy level 2 orbital p with 6 electrons in total. If you count here, you have 6 electrons, and then we represent it there. And then we'll finish with energy level 3 orbital s, and we have the 2 electrons. This one is the spectroscopic notation, also called electro-configuration sometimes. This is how we do it, guys. That is all we do. Now, in this case, you don't need to have the empty spaces, so you can stop right there. For example, that is the electro configuration for magnesium. I hope you understand. I hope it helped. Thank you for watching. I'll see you next time. Subscribe to the channel, like the video. I'll see you next time. Mr. G here.